Okay?
Yep, you're good.
Okay.
היי יקיר,
היי.
כשהייתי ילד היה איזה שיר
אולי כדאי שנדבר על זה?
אני אתחיל בעברית ואני אעבור לאנגלית.
אוקיי.
אבל בקיצור. היי יקיר,
כן.
כשהייתי ילד היה איזה שיר ילדים קצת טיפשי ששמעתי על שפת ים כנרת, ארמון רב תפארת, על איזה ילד שלומד תורה מאליהו. וכל הזמן הייתי שואל, זה הילד הזה, איך הוא נראה, האם נותנים לו לשחק, למה אליהו מלמד אותו? טוב, עברו שנים, אני לא ילד, וזה לא שפת ים כנרת, זה האוקיינוס השקט, ואליהו אין לו זקן לבן, יש לו שפם שיבה, ומעשן סיגרים, מה שאליהו לא עושה, אבל אתה מלמד אותי תורה, אז תודה רבה. So let's switch into English.
Okay.
Uh, there are some, I see recently some developments in your thinking, and let me see if I understand correctly. I mean, you're advancing in two realms. One is the development of the two-state vector formalism, in which you derive all kinds of very interesting results, which are verified by laboratories, wonderful. And the other is your attempt, of which I never felt easy, to restore the particle picture in quantum mechanics, rather than
the Heisenberg approach
the Heisenberg at all.
compared to Schrödinger.
Yes, with the addition of time of the system being affected in both directions of time. And I think I see two developments in both realms. So let's talk first about the Heisenberg picture. For many years, you told me that you can't stand the thought that a particle is in a superposition. And the picture that you saw, the Heisenberg picture, is that the particle has a definite position, although we don't know it. And then with this modular momentum, this is how we see all kinds of
And also modular energy.
modular energy and so on. But then I understand, and this was only recently, that you are now generalizing this approach. You have been tolerant so far to the possibility of superposition of momenta, of superposition of spins. You said, with this I can live. But do I understand correctly that now you are consistently applying your approach to, because this is new, and I don't know whether it is in any of your papers, that even when I ask you about a spin, you say it looks like it's a superposition of a spin, but actually there is a definite spin and no superposition. Am I correct that you now generalize your approach?
Suppose we know that the spin is definite in the zeta range. Then if I have spin and pulse direction, I can also know the spin in another direction. So the spin in the same direction, the question that you ask, is it definite that I don't know, or is it in superposition? Right? Let me think for a minute. I was thinking about. I have it, the spin in the direction. I have an angle in the perpendicular plane that I know this angle, I know what is the spin. But if this angle is completely uncertain, I have no information about the spin in the perpendicular direction. So I say it's completely unknown.
But still,
Wait, but I have to say that in the higher picture, I would say that in the perpendicular direction, the particle is I have to replace the idea of superposition by the idea of the particle in some unknown direction. Uh,
question is, should that be like your treatment of position to say that actually this thing is not superposed, it does have some definite value, but it is only that we don't know it.
yeah.
Is this your approach now? Is this what you would like to do?
But I have to worry about which measurements. That is
Ah,
it.
oh, that's
Uh, if I know sigma d, the width measurement of sigma is exactly zero. Uh,
why is that? If you prepare the particle in sigma c, and so it's up or down, then what do you know about about this, the the sigma x?
so if I measure sigma x, I have equal probability.
Okay, you measure sigma x. Okay.
I have equal probability to find it plus or minus.
Mhm.
But if I do a width measurement, the question is now how weak it is. And if I go to the limit of the strength going to zero and then somewhere is infinite, then it's consistent to say in that case that there would be absolutely no difference between saying that the spin is definite but unknown position.
Mm. So
You see, the general Heisenberg picture tells me that if the particle is described as some vector, then every operator can be written as a sum of a part of it, which is completely known, and another part which is completely unknown.
Mhm. But for you, the unknown is unknown to us, or there is something which exists objectively and we just don't know. Because in the case of position, it is unknown. We call it unknown, but you say it is unknown only to you. But in reality, it goes either through the left slit or the right slit. So that's another kind of unknown. My question is, are you going to be consistent and say that this holds for the other unknowns? Let me even go to the first uncertainty. So you have position and momentum.
Yeah.
So if I know the position, now the momentum is superposed. Would you now say that you can stand with thought that there are many momenta, but again, you think that there is one momentum objective, and it is only that it is unknown, so you will treat it as you treat the position.
Going from the past, when I have a definite position, I have a complete uncertainty of the momentum, right? But I always have a possibility in the future to measure the momentum and to say that that information tells me already what was the momentum in the beginning.
Okay.
So,
Okay, I see.
so just because of this new potentiality, I tend to think about the momentum definite and unknown to me, and I think by doing that extra measurement of momentum in the future, and I say I go back and say that was already the momentum definite now.
Okay.
So it is quite subtle. Uh,
Subtle but beautiful, because
Mm.
subtle but beautiful,
Yeah.
because now actually you're using Heisenberg, and Heisenberg is the person whose philosophy was that forget about objectivity. We have these propositions and so on, but then you use Heisenberg in order to say there is a definite position, the particle, it is only unknown to us. But now, and you do it without violating the uncertainty principle, because you say, if I measure position at the beginning and momentum at the end, in the middle, I know both position and momentum, which Heisenberg thought is completely impossible, and you show that it is possible without violating the uncertainty principle, because you know it only later, and only weak measurement tells you enables you to outsmart the uncertainty principle. And then you can do it also with other uncertainties, so all kinds of spin. But I would guess if
yeah. If I know the spin in the z direction, and I want to say that the spin in the x and y direction are completely unknown. But then I can decide later to whichever I decide to measure later, go back and tell me, look, it was already definite at the beginning.
yeah, we are not supposed to talk philosophy today, but here is a philosophical question which
Yeah.
always I I hate it, but you like it because you say the following. You say that I measured the spin, and now I don't know whether I'll measure later the spin y or z.
You
I
measure
this.
initially in this,
Yeah,
okay.
and then I don't know what will be the final one, whether it will be y or z.
Mm.
And you always say, although I don't know, I'm the experimenter. The particle already knows.
Yeah.
I hate it. But the particle doesn't tell me.
Sorry?
Is it? But the particle doesn't tell me
Tell-
what
tell
what,
me.
what it knows. It's
Yeah.
it's a damn little particle, and it knows even what I don't know.
Right.
And even if I change my mind at the last moment and say, you know what,
Now that you
that I'll
able
change
to
my
tell.
mind. Yeah, I hate it, but you think that this is what gives people freedom of choice.
That's a good idea. It's something very deep, but it's true. Yeah.
That the future is already there in many cases, but because we don't know it.
No, it's not already there.
Yeah.
Because I have not been there and I have not made up my mind.
But for the particle,
So the part is already there.
a particle knows more than the physicist.
More than the, yeah.
Ah,
More than the whole community is.
well, one day I'll get used to it, and perhaps, or I'll have another argument against it. But let's return to physics because, okay, because so this is the first achievement of the two-state vector formalism. I see here two achievements. One is that it is possible to outsmart the uncertainty principle
Yeah.
without violating it,
Right.
because you do it in a very subtle way. Another thing is that the problem of non-locality gets a very nice solution here because people are troubled by the fact that measuring a particle in one place.
You know, the other time on the slide, and if you think it's the one vector, then you say there is really no local tension at the distance. But if I look at it, if I say that the two particles are separated, they already know which direction I'm going to measure for each one of them in the future. They can come just with classes and
Yeah, so let me explain it to the viewers. And again, it annoys me terribly, but it's consistent. I mean, we have two particles which are entangled, which separate them. Here is Alice, here is
yeah.
Bob, and they don't tell one another, and they even themselves do not know which the spin direction they are going to measure.
They know.
No, sometimes even Bob and Alice do not know. They
Yeah,
are not decided.
but the particles know.
That's it. That's it. So, and this is how John Bell found out that there is some non-local interaction with it. And you say, oh, I have a cheaper solution. The two particles, when even before they parted, get information from the future, which is going to be Alice's choice, which is going to be Bob's choice, and then they don't need any non-locality. Just
Yeah,
they know
they
it. And
don't. Wow.
so, can I say in the language of relativity theory that what looks like non-local in space in 3 dimensions becomes local in 4 dimensions when you allow things also
Yeah.
to go through the past. So this is the second achievement,
Yeah.
the two-state vector formalism, is you make things very simple. And although the
No,
philosophical
it's not trivial to say that
Oh,
the thing comes from
it's
the future.
everything but Freudian. Freudian is not.
Yeah.
I agree with you. But here comes what I think is the most revolutionary achievement of the two-state vector formulation. You say that the particle is affected by both the past and the future measurements, the two boundary conditions.
Yeah.
We know only the past, we don't know the future, but the particle already is affected by the future measurement. But then you proceed and say the following. Sometimes the pair of pre and post selection is rare. Usually we have ordinary, say if I throw a particle this way, in most cases it is going to end up either here or here. In very rare cases it is going to end up here or there. And you say select such cases, and then I can tell you that in the middle the physics is actually completely new.
Yeah.
It looks like, so let me,
You need to say that in the middle, the particle, each individual particle can have a family of many, many positive and negative particles similar to it, and they always exist together.
so here comes superposition, which I thought that you eliminated by eliminating the wave, to say no, here, although I stick to the particle picture of Heisenberg,
Yeah.
though I don't need Schrödinger, I still have this superposition.
No,
Because,
you want to this way.
yeah, okay. You have something better than superposition. You say, together with your particle, there are many kind of.
Well, let's take a special example. I have the 3 boxes, and I initially started the particle in left of middle to right.
This is superposition. The particle is either in this box, in box 1, box 2, box
Yeah,
3.
but yes, well, that we write it in the Schrödinger picture. In the Heisenberg picture, I would say the particle is a definite energy state,
In one
an operator that has these 3 amplitudes. Right?
So it is in one of these boxes.
Yeah.
We don't know which.
We don't know which one.
All right. And then you let it evolve.
And then when I do the other thing, postulate,
That is, you open, you reunite the boxes, or what is
yeah, how I could make the postulation be relevant. I postulate that this plus that minus that. Of course, I do it by opening them and simulating them. Yeah.
Yeah. Okay.
So, in that phase, I come back and say now that actually I have one particle in this box, one particle in that box.
2 particles.
and
You began with 1, now you
Yeah.
have 2,
Three, I have 3.
3.
Yeah. One normal particle here, another normal particle here, and here I have the counter particle of the negative particle that has the opposite property.
Opposite properties. So if it is a charge, then the charge is opposite.
Yeah.
Spin is opposite.
The mass is negative.
And here comes the most surprising
Yeah.
thing, the massive negative products. Now, physics has never heard about such a thing, not around us, but you say that for very brief time this state of matter.
Sorry?
You say that, I mean, physics, ordinary physics, doesn't know such
Yeah.
a state of matter. You say that mass can sometimes be negative in these intervals between
Right.
pre and post
It's
selection.
about the end of the
And you got it by simple algebra, because
Huh?
you got it by simple algebra or even arithmetic. You said we began with one, we ended with one, but somehow there was a superposition in all the three. In order to do that, I will say that it definitely existed in one, definitely existed in the second, but existed in a negative way in the third.
Yeah.
And then there is a beautiful experiment, which I'm proud to have been part in one of its versions, in which you can even prove it. You say the following. Uh, let's bring together the boxes in which there is a particle and a negaparticle. The box will be empty.
Hmm?
The box is going to be empty now because
Yeah.
can you
It's
agree?
a red situation.
Yeah.
That is brilliant.
And then when you separate them,
Yeah.
lo and behold,
Yeah.
you will have a particle, and you can continue with this.
Right.
And you showed it with weak measurement, which you like, but you agree that sometimes
It's important that I can make this measurement of each particle, but if I have a large number of them, and I choose a low post selection, suddenly the width value of each one of them becomes a strong value for all of them together. So actually, if I start with n particles, that all of them are initially in a state this one that was dead, and finally this one, all of them, then I will,
this one minus
Yeah.
that third. Yeah.
if it's true for all of them, which is a rare case, then in the middle, I can now see really a world moving in the inside.
So-
It will really be there.
So if we repeat the experiment many times, and we wait for the rare case in which indeed
Or we do slice it.
right, or we do it many times, and then but we keep each of them separately.
Yeah.
And then when we sum them, we say in these cases we got the post selection, then together the collective effect will be that a particle is hit
Well-
a wall, but the wall, rather than being pushed, has been pulled
Right.
inside.
Yeah.
And the delicate question, you and Lev once had this beautiful experiment, which I hope you don't regret publishing, which is the shutter experiment, in which you show that you can validate such a prediction of the two-state vector formula not only by weak measurement, but by projective measurement. What you two proposed was that you took another particle, a test particle, and now you had your particle in the three boxes, and your test particle went to two of the boxes, it was superposed two, and came back. You're okay with that?
Yeah, but there is a simple explanation without with that preselection. It's much more because if I send two particles, it will not act like a shutter and shutter here.
Mhm.
It's only for one.
One which is superposed, which
Yeah,
is split
yeah.
and
But
superposed.
suppose I send two particles, it also
You will ruin it.
Huh?
You will ruin
In
that.
fact, I would see that either the two of them come here or the two of them come there. And it will be a superposition of a pair.
Which is interesting in itself.
Yeah, but that's not the only option. There is another possibility.
This is new.
Then, if I send two particles in superposition, there's a possibility that one of them will come back and the other will go through, or even both of them go through.
Right.
But if they are not going through, then it will be two of them coming from here or two of them from there.
So actually, recently you have another version of this experiment, which is the most paradoxical. You
I
maybe
had I had arranged three so-called shuttles, and they will work in this way. If I send one particle, it will see no shuttle at all. I send two particles, see nothing. Send three particles, all of them will come back.
and this you can do in the shutter version. So the this you can do in the shutter.
No, it's a different bird. And I cannot do it with three boxes. I can either do it, I have to arrange that each pattern can be in a superposition of in two boxes. The first one are in superposition of this box and that box. Second one,
Okay.
this. And if I send, if I select only the upper boxes, and I send the particles there, and I did post selection where it was this minor object, then if only one of them go there, if it comes back, it means that the other must have been there, but the others are not orthogonal because it is flat dead and then it is minus dead. So it cannot happen. That's why it goes through. It's a little bit complicated. Or instead, I can do it with a spin. I can arrange a Cheshire cat that there is no particle here.
So let me just explain. Cheshire cat is the experiment in which, just like the cat in Alice in Wonderland, the cat is in one place and it smiles in another place.
Yeah.
So the Cheshire cat experiment, which has been performed, is a case in which the particle goes along one path, but its spin, just its spin along goes
Yeah.
in
But-
another path.
Okay.
So now you have a version.
So now I have three particles. And each one of them sends its spin to a different location. Then, if I try to scatter a test particle that knows about that is affected by the spin, if I send only one test particle, it will see nothing at all. But if I send three of them, they will be reflected.
And you can generalize it to any number. So this is a paradoxical situation in which you have a particle superposed between several boxes. If you open few of them, it will not be there. If you open all of them, it will be in all of them.
Yeah.
And this experiment can be performed in principle.
Yeah.
It was performed. Shall we have some coffee?
I have also the experiment of their atom.
Yes, I remember. So the atom has a nucleus and
Yeah, this is a very simple experiment
super.
conceptually.
Yeah.
I have a hydrogen atom in the ground state. And the electron, which is in the ground state, has still spin. And I choose initially the spin to be in the infrared.
Okay.
And I write a state, which is the atom either here or here.
The hydrogen.
So, yeah.
Okay.
And in both cases, it's with spin in the infrared.
The spin is the spin of the whole atom, or the spin of the electron.
Of the electron.
The electron.
Becomes the spin of the nucleus is so small you don't see.
You can ignore.
So suppose it's only the electron. And I postulate the state where the atom is in the left and it still has sigma is equal to plus one, but the atom in the right is spinning the opposite direction. Then the width value
In the middle. In the middle.
in the middle. Finding the right atom is zero. But send anything that doesn't depend on the magnetic moment. I check the charge, the mass, there is nothing there. But if I check the magnetic moment. I find there is a magnetic moment there, and it has the shape of the exact wave function of the ground state of the electron. And I have to think about it as the same as I have there a positive and negative atoms. The positive
How
atom,
many boxes?
Hmm?
This time, two boxes or three? How many boxes do you have?
I have two boxes,
Two boxes.
but the funny thing happened on the right box.
Hmm. Okay.
So on the right box, it's not a box, it's just atom sitting there. But that atom is really now the sum of two atoms, the positive atom and the negative atom. The positive, the positive atom has an electron, normal electron with spin in the plus x direction, and the negative atom has an abnormal negative electron exactly sitting together with the positive one, but with opposite spin.
Mm-hmm.
So the charge and the mass
They cancel
of the
out.
two of them cancel each other. The only thing that is left is the magnetic moment of the electron, and the proton and positive and negative cancel each other with an electron.
So, very good. So you had a hydrogen atom, which has
Yeah.
a proton and an electron
Right.
around it. And now it is in two boxes. In one box, everything is okay. But you say that in the second box, if you got your post selection, you have something very interesting. There is no nucleus. The
No,
nucleus. The proton is not there. There is no electron.
no,
That's
no
not
charge.
no charge.
No.
But still,
There is a
the
smile.
magnetic, yeah, the
Yeah.
smile, the cat smile.
But
The
that
magnetic
smile
moment,
as a looks as if something attractive, but that something is not there.
yeah, because there is no
No
proton.
nucleus.
Yeah.
But I know how to think about it. אפשר לדבר עברית, אני רואה שיש...
אנחנו מדברים אבל בשביל המצלמה.
Oh, okay. So I'm saying the one way to think about it, which is extremely mysterious. I just have a magnetic moment floating in space, being reflected to something that is not there. But I have a more physical way of thinking about it, which is the correct, to say really there is something there, but the something is canceling. You have two objects there. One, for example, one positive atom sitting there, and one negative atom sitting there. There are methods of separating them. Then I will see separating
Yeah,
the positive.
yes. This is what you did in one of the other experiments.
Yeah.
Sometimes you show that sometimes a box which is empty,
Yeah,
that is a test particle goes for it times nothing, it's
Yeah.
really empty, but it's not empty. There's been an atom and a negative atom,
right.
and although everything can go through them,
Yeah,
you can separate them, and you say, here's a real atom.
yeah. The with them, only the with the gene. You separate them, you will see here a positive atom, and you will see here a negative atom. Here you will see an atom has negative mass for both the proton and the electron, and the opposite spin. And then you bring it back together so you can do the postulate. So you separate them by strong force, make big measurements, and then bring them together by strong force, and only then do the postulate.
To me, it reminds this surprise that we had about the vacuum. We thought that the vacuum is empty, but then quantum mechanics, the uncertainty principle, tells you that it is actually something very vibrant. Particles and antiparticles.
Yeah, but those particles and antiparticles are both put with positive mass.
Yeah. So in this respect, it is even more revolutionary.
Of course, because nobody thought about negative mass. which cannot exist in the strong energy, but they can exist in the little.
And still, but I have to be uh, somewhat nagging about it.
Yeah.
You think that weight measurements are the best way of validating the predictions of the TSVF, but you do agree that in some cases, like the shutter or even more advanced experiments like that, you can validate these amazing
Yeah, but
predictions.
if I try to do strong measurement, I have another way to think about this is avoiding the thing that the future has to affect the question. I have very simple ways to understand.
But it's still strange.
No?
But it still will be strange. You will say there is a box in which a test particle at T1 went through it, and there was nothing. The same test particle, it was superposed in time, went through it at T2, and there was a particle. And then later, it was again.
But in the case of the shutter, I can say from the one-vector point of view, the particle either was reflected or went through. If it went through, I could not find the post reaction. So, but still the particle could go through, and I will find the future, a different post reaction.
Yeah.
So, but if I, as if I fail to find only that particular postulate, so only the particle is reflected, I can find that particular postulate.
I still think that this can have a two-state vector version, and let me show you how. You have your pre-selection. You don't have your post-selection yet. You take another test particle. It is superposed. You let it interact with the system, and you don't finish measuring this test particle. Then you do your post-selection.
Yeah.
Now that you do your post-selection and you find your post-selection, you can come back to the particle which you left unmeasured,
Yeah.
complete the measurement, and then you'll say, I got the states affected by both pre and post-selection, but now not only in weak measurement. This has been a kind of strong measurement, although a subtle one. Come on.
Yeah.
Why don't you like it? Why don't you? And the reason why I'm asking is that, many people in the community, when they try to, dismiss your claims, which are really exceptional, they say, okay, with weak measurements, there is a lot of noise and so on and so on. I don't think that they are correct. But I think that every once in a while.
But if I want to really show how unacceptable this picture is, I look at the rare cases.
Yeah.
When I look at the rare cases of the three boxes, I really find now by robust experiment that in this box there will be n particles plus minus a small as the square root of n, and these n particles will show themselves in pushing walls or with electric and magnetic force and outside gravitational force. So all these things will show that indeed in the third box there were everything behaves as if there are n negative mass particles there.
So what you're saying is that if we repeat the experiment many, many times, and one day some physicist will be lucky, and he will say, in all, I sent 100 particles together, and in all of them, sometimes it can happen, in all of them I got the rare postulation.
Oh, first of all, let's talk about Soto's sperm.
Yeah.
Again, Einstein did not worry if a person can go without thinking Orthodox life. Nevertheless, by Soto's sperm, he showed that if a person goes Orthodox life, then comes back is younger. So, yeah, Soto's experiments are legitimate. And, and the difference between the people that believe in one vector, they will say that look, we know that there is one cell head here, one cell head here, and one cell head. That's how we prepare it. And then if we look, for example, if one of the walls can move, then for each box, the wall will move according to the pressure of one cell and particle. But they say that if I do enough experiments each time on n particles, very rarely I will see, for example, that one of the walls can move as if there were n particles there. But that motion is due to the uncertainty of the motion of the wall. Even if there are no particles there, a wall that is behind that is described quantum-mechanically has very, very small uncertainty in position and very loud uncertainty in momentum, but still small uncertainty in velocity because it's not. So such a wall, even if the box is empty, we say usually it will keep still. But because it has a wave function, this is very rarely we can find that it moves.
Right.
And moves, moves again, and each different motion will be still much, much rarer. There is no correlation between all these two. So all these things will be all mistake.
Yeah, which is ridiculous.
Huh?
That will be ridiculous.
No, it's true that there are such mistakes. And usually there will be mistakes because there will be no correlation between what happened in one book, what happened in the other book, etc. But if we postulate that all of them being in this or that minus that has a probability of 1/3 to the power n. It's much, much smaller probability than the probabilities of mistakes. But if we do find it, then all these mistakes now are false.
Yeah, this is ridiculous.
Yeah.
That will be ridiculous.
Yeah, but they will say, but that's their fact. They will have to say it because they don't believe that the thing in the future affects them. From the past, it will remain always 1/3, 1/3, and 1/3.
Right. This leads me to another work of yours, which I don't understand, but you have very interesting achievement recently. This is the super oscillations.
Yeah.
This is also related.
Connected.
Yeah.
Because superposition is exactly the state that you find if you have a pre-selection post-selection that are rare. And you ask what is the state of the pointer that was happened to the system.
Mhm.
That is the super oscillation state. It's rejecting the standard Greek mechanism.
Right. There is a work of you and Sandu and some others in which it was amazing. You placed a photon with very low energy in a box,
Yeah.
infrared or whatever, and under certain post selection, you got an ultraviolet or whatever.
No, that was not a, it's a state of a proton I don't need consider. I just start with the state of a photon, which is a position of very, very low moment. Only this, only low moment.
Only low moment.
Yeah.
Momentum.
Yeah,
Many,
momentum,
yeah.
yeah. And if I prepare the right superposition, which is very, very funny amplitudes, very large positive and negative amplitudes, but all of them were very long.
The mathematics is very complex, I understand.
It's not very complex. I can, yeah, mathematics, that's the thing I discovered by considering what happened with this weather. But anyhow, if I prepare this state and I open a hole in the box at the right location, out will come paper. Ultraviolet photon.
About energy conservation.
Yeah, it's violet and
It does violet energy conservation.
yeah.
I think we have earned our coffee.
Huh?
I think we have earned our coffee.
Yeah.
Yes.
What happened though?
Yeah. We were promised coffee, and I think that we have earned it.
Gayatri? Is the coffee ready?
You ready for it now?
Yeah.
So
It's been ready for a while. But
I believe we have earned it.
Yeah.
Probably cold by now.
We're getting it. I just have to get the water and I'll set it back.
Dad, did you find the letter?
I'm still working on it.
Ah, okay. Maybe Abby can remember the language.
I can.
Huh?
I'll find it. I'll definitely find it.
So that one was excellent. So just
And,
change the
what about the phone? Did you send it?
Yeah, I'll just do that.
Huh?
I can do that quickly. I'll stop looking for the letter for Avi,
Okay.
just send that form right away. It's a good point.
So there's a no mathematics actually involved in the
Yeah.
super. Uh, so this is why your collaboration here in Chapman is mathematicians also.
I can write the formula. But, okay, very. Once you know the way to write it, everybody can do it.
Hmm.
Uh, the limit. I mean, we found a sort of solution to the uncertainty of the energy, the conservation of energy, the thing that prepared that state knew to get this energy if we open the thing.
Okay. Can I?
But I can start a state of the whole universe and I can prepare it. So I can say for the whole universe that I start in this initial state, that I can explain where the energy
Of the Big Bang.
the whole Big Bang can go.
Did you present it once to
Huh?
cosmologists?
I
Did
did
you?
not promise it yet.
It's about we should. It's very interesting.
Yeah.
So, so cosmology is pretty good to be it for you. But then let me understand. Now I think I understand something about super oscillations. Can you say that the energy, the extra energy that you get, you actually steal from the past? I mean, you said something about the preparation of the system. So perhaps there was some energy about which we didn't know, and by your post-selection, you actually come back. Like the Big Bang. Yeah, this is the Big Bang of the.
Yeah.
Oh, now I understand it. Thank you, Yakir. So, I'm not talking about the whole universe, but now I understand that by allowing the effects of measurement to go backwards in time, we can pump energy.
Yeah. Yeah.
Thank you, my dear.
Thank
These
you.
are hot, so let me put them
So,
down on the
yeah.
table. Or here's the table.
Ah, there is a table. Let me bring it here. Yeah.
Yeah, right, you
Mm.
can find that.
Thank you.
There's no sweetener. Do you put sweetener in yours?
Anything, honey, something like that. Yeah.
I have some.
רק עכשיו אני מבין משהו, וזה מאוד, מאוד יפה. הייתה עבודה כזו לפני איזה שנה או משהו, שפתרו איזו תוצאה יפה של סנדוויץ', ואמרו שבעצם זה הולך. לא, זה בעצם היה לעשות לו אקסליישן.
This is the farm. This is from the farm, local farm, this honey, and it's processed by centrifugal force, so there's no processing. They're all organic bees.
My dear Gayatri, you are magician. And did Gayatri make a picture of you?
Not yet,
So-
because we've been all busy, but I would love to do that for sure.
Yeah, if you have time.
When
Okay, nice. Spot.
we have alone, and we thought, well, today and tomorrow are good times because everybody else is busy with holiday.
Mhm.
This is a great time to do physics, and then I can have you hold a paradox in your head,
Okay.
in your mind, while I'm drawing you. And that would stimulate coherence in the brain to open up deeper levels of intuitive thinking
Okay.
while we're working. You see what I mean? And then you can draw your paradox and the symbols and write it. Like, see, I did with Andrew. He
Yeah,
held
good
that
job.
paradox in
Yeah.
his. He held onto that paradox while we were working, and then he put it. He wrote it in. Wrote it and drew it in.
Mariam, his wife, is going to love it.
Oh yeah, I'm sure she will.
Mhm.
Yeah, I'm sure she will. I mean, we had actually an artist. I was drawing it in the bar. We had a retreat in Big Bear, right? They invited me to come and give I did a creative visualization with the whole group to develop deeper levels of intuition and utilize creative intelligence through the use of paradoxes, which opposing views in the brain cause cognitive dissonance, and that causes the brain to start scrambling and use all different parts of it to resolve it. And when it does that, it produces these what they call gamma rays, which are the out of the box expansion.
Gamma, it's a brainwave, not a gamma ray. That's a particle.
Brainwave.
Gamma-
Gamma brainwave.
gamma.
Yes, sorry.
I know.
I always leave that
It's
out.
crazy, but not that.
I just take it for granted, but it's a gamma brainwave. Yeah.
Mm.
And it actually uses alpha 1, theta, delta, and gamma simultaneously, and that opens up a deep creative intuitive spaces. It allows for the brain to have coherence, total coherence.
You don't need any sweetener?
Huh?
Honey or
No, no.
So Yakir,
Very good.
thank you, because I've been working on these experiments to develop them because you asked me to at Perimeter.
Okay.
And I've been doing them, and I'm trying to keep on doing them in different settings. So this is the retreat with John Howell, Matt, Justin, all the graduate and postdocs, Jeff and myself, and Andrew. We all did this retreat up in the mountains, and it was
Yeah.
great.
Yeah.
We want to do another one in Ronciglione in Italy, but maybe in a couple of years. We have to get to that. But all art, creativity, and physics. Creative paradoxes, physics paradoxes produce the same type of cohesion. Brain cohesion.
Many thanks.
Yeah, and it's been working. I mean, people.
Very good.
I want to create a system so that it can be used by people in the sciences and physics. So, as Yakir said, art and physics are on the endangered species list. besides our species is on the endangered species list. I mean, we have to start finding new ways to solve problems and with greater global space brain capacity.
Very good. I think that we can now turn off the camera such that we can talk about other things.
Okay.
Oh, sorry.
Uh,
I did.
Now we got everything on camera.
Yeah.
Oh my God.
No, that's okay. Jeff, can you turn it
Yeah,
so that
yeah.
we can talk about other things? חשוב לי שיהיה, אחר כך באתי לך לערוך